Look at the SLS rocket. Nearly 90% of its massive launch weight is entirely dedicated to the propellant needed just to escape Earth's gravity. When every kilogram of cargo costs tens of thousands of dollars to put into orbit, shipping heavy, traditional building materials like steel and concrete to construct cities on Mars becomes a mathematical impossibility. This weight bottleneck forces a complete rethink of civil engineering. We need a structural material that is lighter than the air we breathe, yet possesses the extreme tensile strength of aerospace-grade metal. To build a second home for humanity, we have to completely reinvent how we manufacture and even conceptualize mass itself. The solution is a new hierarchical composite called hydrographene, or HYG, and surprisingly, its origin isn't a pristine lab. Its raw feedstock is toxic industrial carbon waste, petroleum coke, and sludge from Earth's industrial sites. To convert that sludge at an industrial scale, engineers use flash Joule heating. A high-voltage lightning bolt is discharged through the waste, spiking the temperature to 3,400 degrees Celsius in less than 100 milliseconds. This vaporizes the non-carbon elements, leaving behind high-purity graphene. Graphene aerogels are typically brittle, so engineers mix in functionalized multi-walled carbon nanotubes. Think of these nanotubes as microscopic rebar. They are chemically treated to grow microscopic hooks that grab the graphene sheets and lock the 3D lattice together. This specific microarchitecture creates a material with a density of just 5 to 10 milligrams per cubic centimeter. It is literally lighter than air, but it maintains the tensile strength of 6061 T6 aerospace aluminum. We have the theoretical material, but before we can trust it with human lives in the vacuum of deep space, it has to survive a brutal physical stress test. That proving ground is the Moon. The upcoming Artemis missions will act as the high-radiation, low-gravity validation stage for this new infrastructure. To beat the rocket weight limit, Artemis relies on in-situ resource utilization, building structures using local, off-world materials like the abundant, powdery lunar regolith. Small-scale flash Joule heating units on the lunar landers will convert carbon-rich waste into graphene and then mix it directly with that lunar dirt to form Aegis lunar bricks. These bricks are then sintered or fused together using microwave technology to construct completely smooth, continuous landing pads. These black, glass-like surfaces prevent the abrasive, sandblasting effect of lunar dust when subsequent rockets touch down. By turning the lunar surface into a functional construction site, the Artemis missions prove that off-world self-sufficiency is a viable engineering reality. The lunar South Pole presents another massive hurdle: extreme temperature gradients. A habitat can be baking at 120 degrees Celsius in direct sunlight, while its shadowed side plunges to negative 230 degrees. To regulate this, Artemis habitats will deploy Alpha 100 thermal spreaders. Leveraging HYG's massive thermal conductivity of 1,500 watts per meter Kelvin, these continuous graphene lattices act like a high-speed vacuum for heat, equalizing the habitat temperatures without the weight and complexity of mechanical liquid cooling pumps. Then there is the problem of storing fuel. High-pressure tanks are heavy. They are highly volatile. Instead, HYG is a solid-state sponge. This illustrates physisorption. 1.25 nanometer HYG pores trap hydrogen molecules using molecular static cling rather than chemical bonds. Zooming out, this matrix stores 164 liters of hydrogen per liter of solid HYG, allowing rapid refueling without heavy tanks. We now have a material that solves structural integrity, thermal management, and fuel storage on the Moon. The underlying technology is validated and ready for the 2.5-year transit to Mars. Welcome to Phase 3. We leave the utilitarian lunar outposts behind and scale up to permanent civil engineering on the vast rust-red plains of Mars. Mars lacks a global magnetosphere. That exposes the surface to lethal galactic cosmic rays and secondary neutron radiation. If you can't block this energy, you can't build a permanent city. To solve this, the HYG lattice gets a molecular upgrade. Engineers replace the carbon nanotubes with boron nitride nanotubes, or BNNTs. Because of their high boron content, these structures have an excellent neutron absorption cross-section, capturing secondary radiation before it reaches the inhabitants. But the system doesn't just absorb radiation passively.
Because the HYG framework is highly conductive, the actual domes of the city can be wired as massive solenoids. By running a low-energy continuous electrical current through the habitat's shell, the city generates a localized magnetosphere. This active shield deflects charged solar particles away from the Mars bricks, creating a flickering synthetic aurora at the apex of the dome. The HIS system actively repels the lethal Martian environment. It takes a dead, irradiated desert and creates a pocket of absolute safety. Inside that safety, biological life support and hydroponic forests rely on massive power windows constructed from a hydrogenated, transparent form of HYG called graphene. These windows must hold back a 14.7 psi Earth-normal atmosphere against the near vacuum of Mars. Instead of shattering like standard glass, the nanotube-reinforced lattice uses ductile ligament bridging. If a microfracture forms, the internal rebar simply spans the gap, preventing the crack from propagating and maintaining the pressurized seal. Furthermore, because this transparent lattice remains semiconductive, it acts as an electrode for thin-film perovskite solar cells. The clear surface of the dome allows vital light to reach the hydroponic farms, while simultaneously generating electricity across its entire surface area. The engineering required to build these majestic, glowing Martian cities is remarkable, but the most crucial part of this entire process happens right here on Earth. The carbon feedstocks for every brick, thermal spreader, and window are pulled directly from our own industrial waste. This is the enough philosophy in action. The same carbon-negative binder that builds a Martian dome for $35 a ton is equally capable of building Earth skyscrapers. By locking our industrial waste into solid graphene architecture, the technology used to colonize Mars becomes a global vault for Earth's excess carbon. Humanity has the raw material and the chemistry to rebuild our world. The path to Mars is paved with the solutions we need for Earth.